Okay, hi guys. My name is Baran. I'm a member of USC Makers. We're an electrical and computer engineering organization here at the University of Southern California. We started off as a club with just 3 engineering students who just had a common passion for electronics and just making things for fun. And since then, we've grown to a club of over 80 members. And I'll just go through here and tell you a little about what we do. Or actually, here's a little schedule. So this is going to be going till 1 p.m. I'll give you a little intro to what we do, and then we'll have a bunch of our members actually show some of the projects that they've worked on, which we like to think align a lot with what Grant Imahara did. We all have a common passion for building things. So we'll have a Q&A at the end of the presentation, but yeah, feel free at any time to ask questions in the chat. And yeah, so I said this a little bit earlier, but we were founded in 2016 by 3 engineering students as a space to promote hardware innovation. We're completely student-led, so everything we do is just stuff we take the initiative for and do for fun. And we've grown a lot over the past couple of years. The picture on the right is actually 2 years old, so we've gotten even bigger since then. Everything we do is kind of centered around these 3 pillars. So the first one is to learn. We do that through our tutorials that we give to all of our members. We have tutorials on things like Arduino, 3D printing, Raspberry Pis, anything like that, designing your own website. And we also have guest speakers come in occasionally, which you can see in that picture. We love to create things. The main point of our club is to basically split up into teams and build projects. An example of that is right down there, but we just love to build things. And that's what makes us all makers. And then collaborate. We work together on everything we do. Like I said, everything we do is project-based. So we all work on teams and we all kind of build up on each other's ideas to make really cool designs and inventions, which is what our club is all about. So now I'll just go into the project showcase. So it'll go into what each one of our members, like one or 2 projects each one of our members has worked on in the past. So we'll start off with Aiden and soft robotics.
Hello. I do think the presentation might need to be refreshed, if that could be done quickly. But thanks, Braun. Cool. So hello, guys. I'm Aiden Leitch. I'm a junior at USC studying mechanical engineering. I've been in Makers for 2 years now, although I like to think that I'm a lifelong maker. I've always liked to build things, take things apart, just like in that video. And Grant Imahara was actually kind of a hero to me growing up. I loved Mythbusters and all those guys. And it was really inspiring to me when I was younger. And I even had the chance to meet Grant Imahara once. On this slide are also some projects I've worked on, but the one I really want to share with you guys today is soft robotics. So you may remember a movie from a few years back with Baymax, a big inflatable robot. So it's actually based on real technology that's being developed in thinking about how we can use novel materials and new paradigms to create a different kind of robotics. We associate robots with metal, bolts, gears, stuff like that. But in the real world, living things that act a lot like robots in some cases are all squishy and tend to be made of soft and compliant materials. And so there's a whole field where people are taking these materials and using them to create new types of robots. And I've explored that a bit myself. So if we hit the next slide here, I have a short video of one such robot, which is a crawling robot that it has 4 legs and can crawl over terrain, but it's all made of rubber. So let's check that out quickly. So as I was kind of saying, a lot of the impetus for soft robotics is based on creating robots that are more like what we see in the real world, animals, plants, stuff like that. And so you might notice on that one, and as well as this grabber right here, that it's kind of incorporating a mechanism that's a lot like our own fingers, where there's a little tendon kind of running down the middle that, when tightened, causes the appendage to kind of curl up around something. And this kind of gets to the advantages of using soft materials to make soft robots, is that you can get them to interact with the natural world and the kind of chaotic world we live in a lot better. So because something is soft, it can easily kind of comply and form around an object, just like right here where it's picking up that lemon. It can kind of wrap its fingers around it, as opposed to just a mechanical robot that just picks up and moves, and, you know, very robotic, whereas this is a lot more organic. And then I have another example on the next slide that shows that you can even get a fair deal of precision, even if you're creating robots out of soft materials that may not be strong like metal, but definitely have their benefits in other ways. So this shows a bit of the assembly of how I put it together. The big purple piece, as well as the red parts of the previous robots I've shown you, are 3D printed using a 3D printer, which is a tool we use an awful lot in Makers. And then with the incorporation of some simple motors or solenoids, you can kind of bring this soft robot to life. I can pick up little objects now. And again, one of the advantages of soft robots is that they can be very delicate, just like us with our soft fingers. We can kind of pick up and maneuver things quite easily. So that's just kind of a brief introduction to a small niche that I've been exploring as a maker. I have a lot of other interests outside of that, which I'd be happy to talk about during the Q&A. So I hope you enjoyed that.
Thank you, Aiden. And next up is Sean. Oops.
Cool. All right, cool. Good morning, everybody. My name is Sean Yamaguchi. I'm a first year and I'm currently studying mechanical engineering as well. For Makers this year, my project is really to design a robot that can avoid and draw lines as well as trap another robot using said lines. But before I started working on that particular project, I worked on a different thing called Project Sea Hunter. It was my high school senior project where two teams really had to design two things. First, an underwater robot called a USV in the shape of a narwhal that we called Sea Hunter, which was able to communicate to a computer whilst underwater. The second thing we had to design was a quadcopter drone that we called Kita, capable of picking up and dropping off the Sea Hunter, as well as kind of maintaining flight in that sense. My specific role was actually not mechanical design, even though I'm a mechanical engineering major, but electrical. So it was really my job to create all the circuits, communication devices, and sensors for both the robots. For Sea Hunter, we use an Arduino to control the environmental sensors. So that's like your IMU, your temperature sensors, your pH sensors, and whatever else was on that. And a Pi to give us vision and track the opposing USV. Sea Hunter also made use of two pretty powerful motors called T200s that gave us a pretty solid amount of thrust, considering that this particular USV was about 3 to 4 kilograms in weight. On the other hand, we use a pretty typical quadcopter design for Kita. So, 4 motors, 4 ESCs that control the motors, a flight controller, and some semi-weird components that we may or may not have blown up like twice over the course of the year. I would give you guys the circuit schematics for both of these designs, but my Google Drive got deleted recently, so I don't have those images anymore. So that's fun. On the right, we have the CAD for our Sea Hunter, as well as a quick video that kind of shows a test of our quadcopter semi-struggling to pick up Sea Hunter, but ultimately getting it up. After the video, the drone kind of crashed, but we don't need to talk about that. So anyways, next slide. Here's a couple more pictures of what exactly we did. On the left, you can see the actual final products that we were able to design, the bottom being Kita, the quadcopter, and the top being my best attempt at getting a picture of our Sea Hunter. I should also note that we fully 3D printed the Sea Hunter. So that included like the entire body, the mast, and the thing on the right, which is kind of one of the cool things that we were able to actually make. More specifically, the thing on the right is a oscillating tail that kind of goes up and down and moves in like a very fish tail-like motion using a servo and kind of like an angled axle. We also created a narwhal horn that you can kind of see in the image on the top left that held all of our main sensors and communication equipment that was also able to go from fully horizontal to completely vertical. At the end of the day, though, I'm really proud of what we were able to do, especially considering that we were doing this project during COVID and, you know, things didn't always go well, but it's an experience that I'm really, really proud and lucky to be able to have been a part of. So yeah, thank you.
Okay, so hi, I'm Devin. I'm a senior studying computer science. This year, I'm a project manager for Makers. I have a question. Why is boba so expensive? Like all the ingredients end up costing only a few cents, come on. So I wanted to build a robot that can make me a drink without costing an arm and a leg. And so, next slide. What better time to do that than at a Hackdown? For those who don't know, Hackdown is an event where people spend a weekend or so building a cool project instead of doing homework. So I came in with this grand idea and an amazing team to build this thing. Next slide. My original idea was pretty simple. There'd be boba and tea up top. There'd be a motor to dispense the boba, a pump for the tea. There'd be a cup dispenser, because why not? You'd be able to order yourself a cup through an app. But I find that hackathons are a great way to show the engineering design and problem-solving processes to its extremes. Next slide. So constraints. It's really hard to build things when all there is to build with is literal junk. There was a lot of dumpster diving involved. A lot of trash was recycled to create this beauty of a machine. The previous designs could have worked if we had like a few $100s, larger team, I don't know, maybe like more than 2 days to work on a project. And so we had to scrap a whole lot of our design. We had to move to tea because cardboard wasn't strong enough. Our cup gripper system kept failing, so we had to use a ramp instead. And we didn't have a correctly sized funnel, so we had to use a plastic water bottle for the boba. And we didn't have a conveyor belt, so we built a car system to move the boba instead. Because of all of this, our software stack also became increasingly more and more complicated, and we had to rely on multiple ways to transport messages from every client to keep the state machine up to date. But, next slide. But wow, is this not the most beautiful piece of cardboard engineering you have ever seen? Come on. Let's go into the demo. So we designed the car system to catch a cup, and then it would move into the next part where it would dispense boba into the drink. This would work using a servo motor that would just keep vibrating back and forth to invigorate the boba to drop out of the water bottle. And then finally, it will move on to the pump where it will dispense the tea. Yeah, So next slide. And so I guess to conclude for this project, was there a lot of questionable design choices? Yes. Were there a lot of bad code? Undoubtedly. But I guess engineering design isn't necessarily about perfection, right? It's about trade-offs. And at the end of the day, it's about building something you're proud of. Was I proud of this project? Yeah, definitely. And I hope it inspires you to make with whatever you have, constraints and all. Thanks.
Thank you, Devin.
Hi guys, I'm Elizabeth Finley. I'm a freshman and I'm majoring in chemical engineering. So I know a lot of these projects are about making things, but I decided to do a research project that I did my senior year. Because as a biomedical engineer, I'm really interested in prosthetics. In order to make those, you need to understand how the human body works, and that involves a lot of research. So my senior project was research about the scaphoid bone, which is a bone in your wrist. And like you can kind of see it in the left picture where that is, but basically if you hold up your right hand, you kind of like, I'll like flip it. It's like right here is your scaphoid. I actually broke my scaphoid, so this is like a scar from it, so I can help you see it. But for this research project, what I was trying to do was trying to figure out like how the way we fall affects the force that our scaphoid experiences. Because it's one of the bones in our wrist that easily fractures, especially if you go like this when you're falling, like you just go forward. And that's how I broke it. So in order to do that, I created a model of the wrist. It's picture of the model is in the right image. It's a very non-specific model because basically with the technology I had, you couldn't really like make it really complex, or else it just wouldn't work. So what I did instead was I separated the scaphoid from the rest of the small bones in our wrist. So the scaphoid is like the little piece that you see in comparison to the larger orange piece. And then I just chose some of the tendons that are connected to the scaphoid that really affect it in order to help look at the forces that our scaphoid experiences. Can you go to the next slide? Great, thank you. So what I did with this model is I really did 4 different experiments. So one of them was like different angle experiments. So if you can see in the left image, it says 0 degrees. And I'm looking at it now, I probably should have chosen a different image. But basically what I did is I would like rotate this model. So the 0 degrees was like one of the first places I started. But then what I would do is like I would rotate it to the right so that it
Sorry, I think her internet cut out. Let's just wait a second. And
so I'd like raise up the scaphoid up and down in comparison to the blue boxes you can see. Oh, can you hear me? Because it says my internet's unstable. Okay, sorry. So in like the top right picture, you can see that's just a picture of my height experiment. So I would just raise up the scaphoid or raise it down in comparison to where the blue boxes are. And again, I would just do different tests and see what the max force was there. And then my last experiment was the bottom right, and that was, I called it block experiments, but basically what I did was I rotated the angle of the block in comparison, like the normal horizontal line. So if you can see, I wrote 5 degrees on here, and that was like the angle of the block in comparison to just a straight line, like a straight table. And I would rotate that to like 45 degrees one side and then 45 degrees the other side. So basically to sum up, what I did a lot of tests, and what that led me to see was just like how exactly like different angles, different heights, just overall different like block levels affect the force that our scaphoid experiences. And knowing that, I didn't make a prosthetic, but if I wanted to, this research would help me a lot more because I actually know how forces change on the scaphoid. So like this isn't really making anything, but important thing to know is that if you're trying to make something, it's really good to do research so you actually know what you're doing. Because making like a prosthetic with no knowledge of the scaphoid, it probably would not actually resemble a wrist, which is not really helpful if I'm trying to help people who need like artificial wrists. So yeah, that was just something I did. And it was just a senior project I did, and honestly, really what you just need like a little platform where you can make models and just do tests. And it honestly it was a lot of work, but it's really not as difficult as I think I made it seem. But in order to help it out, I have a video that I made. It's like 10 minutes, so I didn't like put it in the presentation, but I can send the link in the chat if you want to look at it. But yeah, that's basically what I did.
Thank you, Elizabeth. And next up, we have Ron.
Hi everyone, my name is Laurent. I'm a junior studying electrical engineering at USC, and I'm actually newer on the Makers scene. I only joined Makers last semester, but one thing I really enjoy about the Makers community is that there's a lot of room for working on projects that are not strictly utilitarian or practical, and we like to have a lot of fun. So the project I worked on last year is Wizard's Chess, which I'm sure many of you are familiar with from Harry Potter if you've seen it. This iconic scene on the left here from the first movie where Harry and Ron are playing. For those of you that don't know, it's basically a chessboard that you can like say your moves to, and it'll automatically move the pieces, and then the pieces that get destroyed when they get captured. So we basically tried to make our own version of Wizard's Chess. And as you can see on the right, it was somewhat successful. Our piece breaking mechanism is not quite as spectacular as in Harry Potter, but I think it was pretty cool nonetheless. So to get into some of the design of it, if you could go back a slide, Ron. Before we talk about our mistakes, because let's not start with that. So the mechanical design you can see on the left is kind of like this XY plotter that you might see kind of similar to like a 3D printer or a CNC machine. It was inspired by a YouTube video of this guy that built like an automatic basketball catching hoop. Basically, you could throw the ball anywhere you wanted and it would catch into the basketball hoop. So we took a lot of the mechanical design from that guy's video, and you can see that there's this H-shaped belt that is connected to two motors that will, depending on how the two motors move relative to each other, it will move this this XY plotter around however you want. And then I actually worked on the electrical team. You can see on the right side some of the components of the very messy electronics that we used. The main controller we used was a Raspberry Pi. You can see that in the top right corner. We also used some voltage converters, power relays, which are basically like electronic switches. And we used an electromagnet. So the basis of the movement was we'd have a magnet underneath like this glass surface that would latch onto the piece and then move it around to wherever we wanted. Yeah, next slide. So in all engineering, you're bound to make mistakes. And one of the biggest mistakes we made is that we hooked up the drivers wrong for one of the motors. So one of the motors just didn't even work. And this was going on for an entire semester before, probably like a semester and a half before we realized what was wrong. And we spent quite a bit of time trying to fix the issue with like using a color sensor to calibrate the motion. And it just really wasn't going the way we wanted it to. It just kept like messing up and like going off diagonally. And in chess, you have to be pretty precise because there's a lot of pieces, and you every time you move a piece, you might like bump into another piece. So there's not a whole lot of room for error. So we spent a ton of time just like trying to figure out how to coordinate these movements. On the left, you can see one of the things we tried, which is we made like a colorful calibration map for the color sensor to go over and like kind of detect where it is on the board. But eventually we just figured out that one of the motors was not working. And once we fixed it, everything was moving really smoothly. So basically don't make assumptions, because just because something worked kind of well doesn't mean it actually worked like it should. So you always have to be very vigilant about like double checking your designs and make sure you have multiple eyes on whatever you're working on. Part of the reason this wasn't caught for so long is we were virtual. So the person that actually had like the in-person board set up thought everything was correct. And then it turns out it wasn't. Yeah, so just to go on to my last slide. The way this worked is you would have this web interface where you could either like click to move the pieces, or you could like record yourself with like a voice command, and then the AI in the background would like decode the command and turn it into like motor movements so that it would move the piece that you wanted to move. And yeah, it ended up working really well. So I was very happy to be on this project.
Hi, everybody. My name is Emily. I am a junior studying electrical and computer engineering at USC. And on Makers, I am currently a project manager. So the project that I'll be showing you today is actually a hackathon project that I worked on a couple weeks ago, actually with some of the people in Makers, which is a lot of fun. For those of you who aren't familiar with the term hackathon, you know, Devin's project was also a hackathon project. You're not actually trying to hack into like the mainframe of anything. You just take like 2 days or 1 day to make a project of your choice and try to get it to work as best you can in that short time. So this is about like a 1-minute video. So it starts with the demo of our project.
Introducing Bark Alert, the service animal emergency response tool for individuals who suffer from epilepsy and seizures.
Hello. Your loved one service dog is trying to get your attention. Please check in on them.
In the United States, it is estimated that over 2.2 million people are currently suffering from epilepsy. A common service for individuals suffering from epilepsy is seizure alert dogs. One thing service dogs currently cannot do is make emergency calls or texts.
The casing houses a Wi-Fi enabled ESP32 and a battery so it can be carried by the user wherever they go. The dog toy is connected to the ESP32 and will function as a wearable that the service dog has EC access to. Should the user suffer a seizure, the service dog can bite down on the toy, which will send emergency contact messages or calls depending on the severity of the emergency.
Your loved one service dog is trying to get your attention. Please check in on them.
When the bone is pressed, a request is sent to our Flask web app, which is hosted with Azure App Service. The app checks an Azure SQL database to determine who needs to be contacted, then calls and texts the necessary people with the Twilio API.
To enable texting and calling features to their emergency contacts, they would first log into our web app hosted on Azure websites. After logging in, they can select whether each phone number is okay to call or text, and then this number gets added to an Azure-hosted database.
One of the major unique benefits Bark Alert provides their customers is a sense of independence.
Okay, so sorry, I know that goes a little fast. We had a tight time limit for the video submission, but basically to walk through that a little bit more slowly is we made this, which I have right here, this little 3D printed casing, and it just emergency notifies people. A lot of people struggle with seizures and other conditions and have service animals. So basically it allows the service animal to bite down on this bone that we made. And then that pressing down on that bone will send a call to a designated emergency contact, which was a lot of fun to work on. So again, we kind of did this over the course of a couple of days. One of the fun things about making is it is such a collaborative effort. You kind of get to get your friends involved, work in a team, and just try to make whatever you feel like making, whether it's for fun or for some kind of social good purpose. Personally, I really like making like small wearable devices for kind of social good purposes. It's kind of my niche in the making world that I've seen, but it's really fun. You'll definitely bump into a lot of issues. Like for this, we spent like 3 or 4 hours trying to debug button pressing code, which is like the simplest part of probably the code that we were making. And as it turns out, like it was like similar to Laurent, how it was just a motor that wasn't working. The breadboard itself, which is what you connect wires to, was broken for some reason. So it's always fun to find those kinds of little issues that you'll spend like 3 hours working on and realize, oh wow, the whole time it's been this. But just like to walk through our enclosure, it's this 3D part. We've got batteries here. Right now it's turned off. Since it's a hackathon, we didn't consider the fact that you need like an on-off switch. So it's just on all the time until you put your batteries on. So I can just turn that on right now. You can see it running. Right now, the partner whose phone goes to isn't available right now. Also, one of the soldered connections broke a little bit ago because I sat on it. But overall, you can see these little components, and it's a lot of fun. So I definitely would recommend doing hackathons if you have the opportunity to, or just making small projects with your friends and getting involved, even if you feel like you don't really know what you're doing. You'll learn on the way, and that's probably the joy of making. Thank you so much.
Awesome. And
Introducing Bark Alert.
on a much less serious note, one of the projects that I worked on in Makers was called Robinaldo. So if any of you have heard of the game called Rocket League, that's what the project was kind of inspired by. So just if you don't know, it's just a whole bunch of cars that drive around and try to shoot a soccer ball into a goal. It's a really popular video game right now. I mean, yeah, a lot of our projects are just like that. They're just inspired by fun things like video games. Laurent's project was just inspired from something from a movie, Harry Potter, Wizard's Chess. We've had stuff inspired from like Rick and Morty movies, Parks and Rec. We had one called DJ Roomba that was inspired by that as well. So a lot of our projects are just fun things that we see in a TV show or whatever, and just decide that we want to make it for fun, which is, I think, the essence of making and why it's so great. You can, it takes time, but you can kind of make any sort of dream you have or like any sort of thing you see a reality. So this is our take on Rocket League. So I know it looks not as spectacular as what you saw on the last slide, but this is basically a robot we were designing that would be able to take up a soccer ball. So that's what this part of the robot right here is for, and shoot it on a goal. So this is like a CAD, which is like a computer assisted design model of our robot. And here's a little video of it in action. And this is when we first got it to drive, which was really exciting for us.
That's so true. Okay, so what happens when you unplug this? Does it restart?
Don't unplug that.
Yeah.
Do not unplug that, because if you do that, the Jetson will shut off, and so we have to redo the launch files.
Yeah, so I think one of the really fun parts about making in general are these aha moments where you finally get something to work. So we've been working on this robot for a semester, which is a couple of months, and when we finally got it to drive around, that was really huge for us. It sounds really simple and ridiculous, but it took us a lot of time to get to that point. So that's one of the great parts about making is the reward you get to see when your hard work pays off, even if you have to spend hours debugging issues that might seem dumb. In the end, the reward definitely pays off. But yeah, that's all we had for our presentations. So yeah, any of you people who are attending, feel free to ask us any questions now. It could be relating to what we did with our projects or just USC STEM in general or anything like that. So yeah, feel free to unmute or send your questions into the chat.